Hello, good evening. Thank you for joining us for part one of a two-part webinar series entitled The Next Frontier for UCLA Astronomy with the James Webb Space Telescope. Today's program features distinguished Professor Matt Malkan, Professor and Vice Chair of Astronomy and Astrophysics Alice Shapley, and Professor Tomaso Treu. My name is Miguel Garcia Garibay. I am the Dean of the Division of Physical Sciences, and it is a pleasure to welcome you to what I know will be a very engaging program. In my role as Dean of the Division of Physical Sciences, I have the privilege of working very closely with the entire community of our division. Physical Sciences is a division rich with education and research excellence, which has had an enormous impact on the world through its 6 departments, which in addition to physics and astronomy, includes the Department of Atmospheric and Oceanic Sciences, Chemistry and Biochemistry, Earth Planetary and Space Sciences, Mathematics, and Statistics. We also have 4 interdisciplinary institutes and numerous affiliate research centers that round our commitment to the best education and research within the sciences. The Department of Physics and Astronomy is not only the home to a recent Nobel laureate, Professor Andrea Ghez. It is also home to many other top specialists and scientists leading the way into thrilling new areas of research, including quantum computing and virtual reality. Our students and faculty in physics and astronomy are discovering hundreds of new exoplanets far from Earth and solving century-old problems, such as creating the first 3-dimensional atomic imaging of an amorphous solid and shedding light on the atomic structure of gases and plastics. The department's new master's professional degree program in quantum information science is providing a critical bridge between research and industry. Department faculty have been named to the National Science Board as fellows of distinguished institutions, such as the American Astronomical Society and the American Physical Society. Today, we will hear from 3 of those outstanding professors from the Department of Physics and Astronomy, whose work interacts with the James Webb Space Telescope in a variety of pioneering ways. I would now like to give you a brief overview of our program. We will begin with distinguished Professor Matt Malkan, who will help us get an understanding of what is special about the James Webb Space Telescope. I think I should just shorten it and say the JWST in short. So how UCLA is involved using the JWST, why the successful launch is so important and exciting, and how JWST can measure the complete history of galaxy evolution for free. We will hear after that from Professor and Vice Chair of Astronomy and Astrophysics, Alice Shapley, who will share how JWST will enable many unique and unprecedented probes of the formation and evolution of galaxies, like our Milky Way. And we will conclude with Professor Tomaso Treu, who will give a description of 2 programs that will seek to address questions such as, how did the first galaxies form and light up the universe at cosmic dawn? And what is the universe made of? And what is driving this expansion? Well, please feel free to ask questions throughout our program in the Q&A box. We will answer questions live after the presentation. However, Matt, Alice, and Tomaso will monitor questions throughout the program to answer as they can along the way. With that, it is my pleasure to invite Professor Matt Malkan to begin the presentation. Matt.
Thank you so much, Dean Garibay, for that excellent introduction. I'm going to share my screen and give you a little bit of background, although you may know a lot and have heard already a lot about the wonderful JWST. I want to just convince you in a minute that this is the biggest, greatest thing that has happened to astronomers in our careers. And something you probably don't know at all, UCLA astronomers are all over this. It's remarkable, and you'll learn about both of those things. So first, the JWST, this is a very big telescope. This is such an ambitious project. Here it is in the clean room. If you can see my cursor here, this is this partly folded up mirror. You can still see it's 22 feet high and it's 22 feet wide when it folds up out. And then you have this enormous, and this is crucial, 5-layer sun shield, which is about the size of a tennis court. You can see the little workers in there for scale. Where were you on the morning of Christmas at about 4 a.m.? In case you weren't glued to your monitor screen, you might have missed the beginning of the voyage of JWST. Let's see what it is, and you can brush up on your French because it's from French Guiana.
À tous de DDO, attention pour les deux comptes finales. 10, 9, 8, 7, 6, 5, 4, 3, 2, unité, top.
And we have engine start. And
Allumage
liftoff.
UAP, décollage.
Decollage, liftoff from a tropical rainforest to the edge of time itself. James Webb begins a voyage back to the birth of the universe. Punching a hole through the clouds, 20 seconds into the flight. Good pitch program reported.
And I learned a little bit of French there too. What a great Christmas present. Can't get better than this. This is after
And there is the view.
Satellite successfully reached orbit. Then the telescope is now released and sent on its way quite far from Earth. Let's see how that
From
goes.
the upper stage camera on the Ariane 5, looking at the James Webb Space Telescope as it moves gently away
That's the back end
from
of it.
its launch vehicle.
And that's the last iconic view of the back end of JWST that humans are ever going to have, because now it is 1 million miles away from the Earth. This is absolutely the most ambitious technical gamble that I can think of, at least that doesn't involve risking human life, and NASA's ever undertaken. They rolled all puzzle to fit inside the front end of the Ariane 5 rocket is kind of a miracle. Look at how hard that is to do. See, all of the panels are folded up, the solar shields are wrapped around it, and just barely fits inside the top end of the rocket. The launch was perfect, absolutely successful. Thank you, European Space Agency. The second crucial event that people were very nervous about, this delicate but very crucial sun shield is completely unfolded and deployed, keeping the telescope in absolute darkness of space so it can be almost cooled down to absolute zero. That's essential, as we'll see. Now, all of the mirror segments, 18 of them, are fully unfolded and are now being moved in a very complicated process to bring them all to a perfect common focus. That's going to take about 3 months. At the same time, the instruments on the backside of the telescope, I'll tell you more about, have to all be cooled down to extremely low operating temperature. So we're not really going to start seeing data for about maybe the beginning of June, and then it's going to start coming out slowly. But that's when we're going to have an operational working telescope. Now, why all of this fuss? First of all, it's not going to be in a low orbit around the Earth. This telescope is too sensitive. It must be a long distance away from the brightness and the heat of the Earth, but we always want to keep it near us so that it can be in continuous communication with Earth. And there's one clever orbit that it took a good rocket to launch it into, which keeps it about 1 million miles. It's going around the sun. It's not going around the Earth, but it always keeps up with the Earth because it takes about 365 days to complete one orbit around the sun. So there it is being deployed, and now it's going to stay in this relative position. So you'll notice it's always pointing its sun shield towards the sun, as it should, and the telescope is always in the shadow. And the radio antennas and transmitters and things will be in communication with the Earth. And it has achieved this orbit brilliantly. So it has lots of maneuver gas to continue staying exactly where it's supposed to be, actually for a few decades probably. And so that gets another check mark. That was a big issue. So why do astronomers seem to be obsessed about big telescopes? We just have a gigantic glass fetish or something? Well, there's a very good reason, and you may know this. Big telescopes, when you point them in any direction in the sky, you are basically getting a core sample through the universe as far as you can go back. Because if you're looking to a large distance, which a big telescope can provide for you, you're also simultaneously looking back a long way in time. So of course you see many nearby faint galaxies in your core sample, but as your vision goes further and further, you see galaxies that are not as they are now, but as they were billions of years ago, maybe to when they were even first forming. So the bigger the telescope, the greater the reach, the further back in time we can look at this cosmic history. That's really the big selling point for JWST. Move over Hubble Space Telescope. This is almost at scale, I think. There's a much more powerful telescope now ready to do these core samples, drilling through the universe deeper, much deeper than Hubble, so to detect more galaxies, fainter galaxies, further in distance, further back in time. We got one other thing we have to account for, which is we're looking at galaxies so far away that their light set out on its journey in our direction when the universe was much smaller than it is now. It's expanded substantially since the time that we actually observed these fastening up. So there's a mysterious object when the universe was much, much younger and much smaller, sending out light rays in all directions. Some of them just happen to be traveling in a direction which will lead them to hit the JWST mirror. Billions of years later, there's JWST receiving it. But what's happened in the meantime, as this photon, that's the same photon there, had to travel across an expanding space. Look at this little black rectangular grid. That shows you how much space is expanded. It looks like a factor of several times here, maybe even more than that, maybe up to 10 times. The wavelength of the photon that's in transit also expands. The universe is stretched out, the photon is stretched out. And that means that if the photon was initially a visible optical photon that we like to study and we understand those very well, we're going to have to detect it with JWST in the infrared. It's been stretched out so much, we need the best infrared telescope in the world. And that is definitely what's been out of the world. That is certainly what NASA has produced here. This is the bottom side being put together of the JWST. And it's busy down there because there are 4 different cryogenically cooled infrared detectors down here. And this is a schematic of it. Of course, it's not quite color coded right. For example, here's a near infrared spectrograph. Here is NIRISS up here. And you'll be hearing more about these instruments because UCLA astronomers have plans for all of these instruments. Basically, they each are optimized a little bit a different way. But the basic idea is that they can take a direct image of infrared light, and that's very informative at very high magnification with extreme sensitivity. Or, this is even more interesting, they may take the light and spread it out into its constituent colors, and that gives you even vastly more information. The nice thing about this is by design, these instruments are all crammed in together here at the back end of the telescope. So the telescope brings its very faint light from a field of galaxies into a focus somewhere around here. All of the instruments are simultaneously up, looking at the sky as seen by JWST, and they can actually take data, they can open their shutters and measure slightly different displaced regions of the sky at the same time. That was a very clever feature. At least 2 instruments can work at the same time. And we're going to really exploit that in a minute. In particular, we're going to exploit it using this camera in the corner down here, so-called NIRISS. But as I said, UCLA has big plans here. We were, I guess not too, I was pretty impressed, all right. The number of projects, of course, that was accepted by US proposers was only 180. Most of them were rejected. And yet, of this very elite list, this is really the most dramatic competition that you can go through, the JW peer review. 7 of the projects that are selected to be executed in JW's first year are led by UCLA principal investigators, and they're listed here. I mean, this is an extraordinary accomplishment for any department of astronomy anywhere in the country. Today, you'll be hearing from these three people. That's me, and then we'll hear from Alice and Tommaso. And in the second part of this series, we'll hear from the other three UCLA principal investigators. So I put their projects on there too. But now, if I may, I'd like to speak about my particular pet project here that I'm very excited about, and which also has the distinction of having the best astronomical acronym for 2021, PASSAGE, Parallel Application of Spectroscopy to Analyze. Just look at the last two words, galaxy evolution. That's what we want to figure out. And we're going to use a trick. The dean already mentioned this. Because our camera is always looking up into deep space, while some other observer is using the telescope, has been allocated the time to do some very interesting science, I'm sure, do some fascinating exoplanet research with their camera. Our camera, not just going to sit there doing nothing. We're going to turn our camera on and start taking very long, deep exposures of seemingly blank sky. But now you know there's no such thing as blank sky when you're looking anywhere. In any direction with the JWST, you're looking at a deep field. You're going to see hundreds, thousands actually of galaxies at all different distances simultaneously through your core sampled universe. And we're going to do this many times. So we'll look, because the universe is not the same everywhere. So we're going to get many representative random views of what the galaxies look like nearby at intermediate distance and all the way back as far as we can see them, hopefully back to when they were born. And I just have to say this, all of our data comes, quote, for free. Yes, I said for free, no real, hardly additional cost except the cost of reading out the computers and running the electricity through the instruments while the other observer gets their data. What is this, to give you an example, how it's going to look? Here is an image on the left of a little teensy patch of sky, and you can see hundreds of faint galaxies in here. And then we take the same picture of the same region, except on the right-hand side, we've done something interesting, run all of the light here through a prism. And everybody knows, it's essentially a prism. Everybody knows that what that does is it spreads the light of each of these objects out by its colors. That's a spectrum. And now you can see there are two objects there. These two objects appear here, except now we have a spectrum that runs, well, the shortest wavelengths would be very far red light out into the pretty far deep into the infrared. So we're learning a great deal, not just about what the galaxies look like, about where they are and so on, but also when we study these spectra in detail, we figure out what the galaxy is made of and how it works, how it's generating its power. This is really just a little preview to whet your appetite. JW, our PASSAGE program, will be so much deeper than this. Now, what kind of things specifically do you see? So this is just to give you a little feel for what we will see. Many of these galaxies have gas in them made up of elements that we're familiar with on Earth, and they give distinctive glows at particular colors or wavelengths, emission lines. Now, you're going to learn a lot more about this from Alice Shapley, but just to give you a preview of this, each one of these this corresponds to a distant galaxy. I'm just putting a few arrows here to show you the little bright spots here, which we'll identify as coming from hydrogen gas, helium gas, oxygen atoms, sulfur, neon, and so on. So there's an amazing amount of information available in a spectrum. Really, to me, that's kind of the heart of observational astronomy, because that's when you get to really understand the object you're looking at. Of course, it's great to just take a picture of it. That's very important too. But for real astrophysical analysis, we've got to have these spectra, and we've got to have them in the infrared. Well, by the way, why does it have to be in the infrared? That's because the universe has expanded so much since it was young. All of these wavelengths have been shifted to the infrared. And that is why we are so paranoid about any heat radiation, that's infrared radiation, being generated by the telescope itself. You can't do astronomy in a room with the lights on. We've got to have all the infrared radiation from every possible surface minimized as close to zero as possible. And that's one of the drivers of why this telescope is such a technical challenge and such an awesome achievement. All right, so what are we going to do with these deep drilling fields? This gives us, as the dean said, a look at the entire cosmic history of how galaxies have evolved to the present day. Looking back at the youngest, that's the most distant galaxies, and we already have a pretty strong idea of what we're looking for here. Galaxies have changed enormously from when they were born, when they were in their young, early stages, to the way more mature modern galaxies like the Milky Way are. And we want to find out how that's happened, want to measure it quantitatively and understand why it's happened. So I have a number of questions that I really hope, well, we told in the proposal we would answer these questions, so we better answer them. Question one, when did the galaxies form their stars? I mean, to me, that's practically a definition of when a galaxy really becomes a galaxy. It starts out as gas, then the gas clouds in dense regions have more gravity, which causes them to collapse to make stars. Then it's actually gone from protogalaxy to a galaxy. And we see this process still at a very low level scale happening today, even in our Milky Way, even nearby. So just to show you a pretty picture of an example of what we would like to see at great distances, here is the Orion Nebula. This gas cloud has recently produced 4 little stars in there, and they're causing the gas around it, out of which they were born, to glow quite characteristically. It looks kind of pinkish. This is the light from hydrogen gas there, the most common gas. Now, if you take a whole galaxy, there's a nice spiral galaxy. It has these, today, they have these beautiful spiral arms. All of these are thousands of little Orion nebulae where stars are being born in the spiral galaxy. But my second question is, well, that's nice for today, but in the young galaxies, the first galaxies, where did the stars form? After we answer when. And it's going to be very different from this, completely different. There probably won't be spiral arms. There may not even be disks of galaxies at all. Galaxies tend to look like little pieces of shrapnel. Sometimes it's even hard to decide what a galaxy is in the young universe. But one thing I can tell you is that the first galaxies were forming stars much more intensively than pretty much anything we can see today, certainly far more than anything going on in the Milky Way. Now, even though the galaxies are going to be thousands of times further away that we're going to look at compared to this lovely nearby spiral, JWST has such a beautiful magnification. It's above the turbulence of the Earth's atmosphere. It's a big mirror. It's designed to give us enough resolution to map out these galaxies, even at very high distances. I'll put a third question on here. That was interesting to find out. But as soon as we've learned about the stars forming, I want to see what they do. So question 3, how and when did the stars in the galaxies produce the heavy elements? Because you realize a primordial galaxy, and we'd love to find these also, has nothing but material gas from the Big Bang, and that's just hydrogen helium, a completely boring universe. It would be lifeless. We know already that all of the heavy elements that are essential for life, right down to the iron in your bloodstream, must have been produced by nuclear reactions in the first generation of stars. And then they had to be released, recycled by supernova explosions that must have been something like this. And this must have been a very common occurrence when galaxies were just forming their first big generations of stars, probably in bursts. Now, you're going to hear a lot more fascinating details by Alice in a minute on this. They're going to learn so much about this process. It's going to be mind-blowing. Finally, I put my last question with an asterisk here because this is a kind of a personal favorite. I have been fascinated since I was a kid. Okay, not since I was a kid, since I was a graduate student a few years ago, about how do galaxies get these giant black holes in their centers, which can sometimes consume a great deal of gas and stars from the galaxy. And when they get fed, they get ridiculously bright. They become the brightest, most powerful objects in the universe. They're called quasars. And then when they run out of fuel, as has happened today, for example, in the center of the Milky Way, they're just still these giant black holes lurking there. But in the process, how do they get so big? How do they grow? How does the galaxy react to all of that energy being released? We really want to find this out. I mean, there's some fascinating theories and speculations that the presence of this giant black hole as it's blasting energy controls the evolution of the galaxy and maybe stops it from growing and stops it from forming stars. I want to find the actual evidence of that whole story. And the whole is not a pun there. And we're beautifully positioned to do that with our data. But, you know, all of those are fascinating questions that will, I think, have a great shot at answering. But what you might want to ask is, okay, Matt, just tell me what's the biggest discovery. Well, I can tell you what the biggest discovery of JWST will be, although you're going to learn a lot in the talks that are coming up. Because I know, because every time astronomers have had a factor of 10 or 100 times gain in sensitivity, a new way of looking at the universe over what was previously possible, every time that the biggest discoveries that were made by that breakthrough were not predicted by anybody before the observations are made, because we couldn't imagine the phenomenon that we would see. This is just a guarantee. So that's also going to hold for JW. And if I turn out to be wrong, I want you to come back and bug me about it. But you don't have to take legal action, because I'm safe on this one. You can take this guarantee to the bank. All right, so that's what I wanted to tell you about. And now I think Alice will carry on with some fascinating stuff.
Thanks so much, Matt. Thank you for your beautiful talk and giving us such a nice overview of JWST. So just gonna get things going. All right. So today, I want to talk to you about JWST and the origin of the elements. This is actually a story not only about the origin of the elements, but also the origin and evolution of galaxies. That's sort of a running theme for today. But to get started, I want to orient us about galaxies. So a galaxy is an island of stars in space that are held together by gravity and orbiting a common center. And the galaxy that contains our own solar system is called the Milky Way. So edge on, our Milky Way looks like a flattened disk of stars with a central concentration or bulge of stars. And you can note the location of the sun in the solar system far from the center. But more generally, galaxies in the universe today come in two main flavors. There are bluish spiral disk galaxies like the Milky Way here on the left, and reddish spheroidal systems that are called elliptical galaxies that are shown here on the right. And one of the key questions in astronomy today is, how do tiny density fluctuations in the very early universe develop into the rich variety of galaxies of different sizes and brightnesses and colors and shapes that we see around us today? And so there are a few ways that we have of answering this question, and just to reinforce some of the key concepts that were introduced by Matt, one of the key methods that we have for addressing the question of galaxy formation is to use astronomical telescopes as time machines. So as Matt discussed, the finite speed of light means that distant objects and parts of the universe are observed at earlier times. So we can construct the timeline of galaxy formation directly with observations of distant galaxies at earlier epochs, which we collect with an amazing array of telescopes. So I'm showing a bunch of examples here on the slide. They include the Planck satellite here, which has taken the so-called baby picture of the universe in its cosmic microwave background radiation. We have the Keck Observatory, which we use extensively here at UCLA. Then there's the Hubble Space Telescope, which is the predecessor of JWST and which orbits the Earth and has transformed our view of the distant universe with its both sharp and sensitive images. And here on the right, we have the Spitzer Space Telescope, which was an infrared telescope particularly sensitive to dust emission in the universe. So as Matt mentioned, one of the key facts of the universe is that the finite speed of light enables us to travel back through time. And another key fact, which Tommaso will talk about much more in his presentation, is that our universe is expanding. And this was most famously discovered by Edwin Hubble back in the 1920s. So it appears that external galaxies are receding from us and more distant galaxies are receding faster. So this observation is consistent with an increase in the overall size of the universe with time. And also, as Matt mentioned, the expansion of the universe leads to the so-called redshift of photons that are emitted by distant sources. So the universe stretches by a given factor in the time it takes light to travel to us from a distant source, and the wavelengths of light stretch by that same factor. So personally, I study galaxies that are roughly 10 billion years distant from us. And in the time it takes the light to reach us from these distant galaxies, the light's wavelength stretches by roughly a factor of 3. So that means that photons that are produced in these distant galaxies as ultraviolet light are seen by us and our telescopes as visible light, but photons that are produced in these distant galaxies as visible light are shifted into the infrared part of the electromagnetic spectrum. Now, JWST, as you've heard, is an infrared telescope. It is sensitive enough because of its mirror and being up in space to see the most distant galaxies we know about in the universe, observed within the first few billion years of cosmic time. You know, the universe has been around for about 14 billion years, so we're going back to the first few billion years of cosmic time. So JWST is also equipped with infrared instruments, so it's sensitive and it's infrared. And these infrared instruments are sensitive to the visible light that was emitted by these distant galaxies whose wavelength has been stretched by the expanding universe. So because of these reasons, JWST is therefore the ideal observatory for studying the redshifted light from distant galaxies. So as we look back over the history of the universe on this stretched out timeline, okay, you can see the bottom edge of the timeline shows from right stretching back to left, the number of billions of years we're looking back. A crucial period for the emergence of galaxies and their structure is the first few billion years of cosmic time. During this time, the spiral and elliptical structures that we observe in the universe around us today were being established, okay? And here you can see, I'm gonna show you which region I'm talking about. This is the first few billion years of cosmic time. And there are many key questions that we must ask regarding the formation of galaxies during this early time. So a couple of the most compelling questions include the one that says, how do galaxies grow? Or saying it slightly more technically, we could say, how is matter assembled in galaxies? So models of galaxy formation suggest that growth in galaxies is fueled, especially at these early times in the first few billion years, by the accretion of gas from the intergalactic medium. And this process is shown here in this snapshot from a computer simulation, okay, over here where I'm showing with my cursor, okay? And this is a model of how a galaxy that will turn into something like our Milky Way galaxy today. It's a model of how a galaxy might form almost 12 billion years ago. And this would be the nucleus of the galaxy, okay? And you can see that gas is streaming onto this galaxy as it's forming 11.6 billion years ago. Now, in terms of galaxy growth, though, we can also find examples of galaxy collisions. And these are actual images from the Sloan Digital Sky Survey of galaxies merging together in these giant train wrecks. And this merger process also appears to be more common in the past. So the question is, how important are major galaxy collisions versus gradual gas accretion to the buildup of galaxy mass? Another key question that's kind of related is, what regulates the number of stars that are born in galaxies over cosmic time? So why are some galaxies like our Milky Way still sort of burbling along today, making some new stars, while other galaxies like the giant elliptical galaxy M87 in the Virgo cluster, why are they done forming stars billions of years ago? The answer to this question lies with how much fuel a galaxy contains, i.e. how much gas a galaxy contains that can be formed into new stars. The amount of gas that is contained in galaxies is related to how much gas falls into the galaxy, how much gas is converted into stars, and how much gas is blown out of the galaxies. Indeed, unlike the term island universes that was coined by the philosopher Immanuel Kant, galaxies are actually not isolated islands. So simulations, like the same simulation we were just looking at in the previous slide, so these simulations show that galaxies are fueled by infalling gas from the intergalactic medium. Okay, so this is definitely a theoretical picture that seems to be confirmed by the observations where we can make them. And at the same time, we can see direct evidence of gas being propelled out of galaxies back into the intergalactic medium. And one of the closest and most beautiful examples of this outflow process is the nearby star-bursting galaxy called M82 that I'm showing here on the right. And this is only 11 to 12 million light years away. We've been talking about billions of light years, but this one is only 11 to 12 millions of light years away, basically in our cosmic neighborhood. And the red here in this image indicates ionized hydrogen gas that is moving at hundreds of kilometers per second, which is about 1 million miles per hour. And so understanding this flow of gas into galaxies and out of galaxies is one of the final frontiers for understanding galaxy formation overall. And it actually turns out that measuring the mix of chemical elements in galaxies is a powerful way of constraining galaxy growth and answering the questions that I just posed. So why is this? Well, as Matt already gave an idea about, the majority of ordinary matter in the universe is made of hydrogen gas. And after that, the most common element is helium. And I'm just showing you a periodic table that you've probably seen before in your chemistry class. After helium, the most common element is oxygen. And furthermore, while hydrogen and helium and the element lithium were all made within the first few minutes after the Big Bang, the rest of the elements, like iron and oxygen, are actually created in stars and stellar deaths, like supernova explosions, like Matt mentioned. Even there's some collisions of stars that make things like gold and platinum. So if you have colliding neutron stars, it turns out that you can make platinum and gold. But the formation of the majority of chemical elements, and in particular oxygen, the most common one outside of hydrogen and helium, is intimately connected with the formation of galaxies and their stars. So let's look at this in a little bit more detail. Okay, so this graphic here shows the cycle of star formation and the production of chemical elements in galaxies. So on the top here, we show the interstellar medium in its atomic form, okay? And this atomic gas will cool into a molecular form, and molecular gas clouds are the very fuel out of which new stars are born. Okay, and so we see that these molecular gas clouds turn into a nursery for making new stars. And this is the very famous image of the so-called pillars of creation, a stellar nursery. Now, inside the stars, we see basically nuclear reactors. These stars are forging chemical elements in their cores, and a wide range of elements depending on what kind of star it is. And then when the stars die, they release the products of this nuclear fusion back into the interstellar gas through either their outflowing stellar winds in a gentle process called a planetary nebula, or else the very dramatic explosion of stars that we call supernovae. And so what happens is the products of this nuclear fusion get released back into the interstellar medium for the next generation of stars. And we have this cycle of chemical enrichment. Now, oxygen is the most abundant element created in this process. So now let's revisit our standard model of galaxy formation. We have a galaxy growing and evolving in the early universe. So here we have the site of a galaxy forming, okay? So gas falls in from the intergalactic medium. Gas is converted to stars in the center of the galaxy, and then gas is blown out, just like we saw in the galaxy M82. But the thing to keep in mind is that chemical elements like oxygen are an important part of this story. As we just discussed, oxygen is forged inside stars and then returned to the interstellar medium. That's what I was just showing you on the previous slide. And then some of this oxygen is actually blown out of the galaxies in these large-scale outflows. Okay, so if we can measure the oxygen content of galaxies over cosmic time, these measurements can place critical constraints on the ways in which galaxies form and evolve. So how do we measure this oxygen in galaxies? Well, the way that we determine the oxygen content of galaxies is by measuring their spectra. A spectrum takes the light from a source and spreads it out into all its constituent wavelengths, like passing a light through a prism. And it turns out that each chemical element has a very specific spectroscopic fingerprint, a very specific set of wavelengths at which it will create emission lines or else create absorption lines if there's a background light source. Now, for the matter at hand, we care about emission lines from galaxies that are making lots of stars in the early universe. And you can see that the gas cloud in this diagram emits light at very, very specific wavelengths. And these are determined by the mixture of chemical elements in that very gas cloud: hydrogen, oxygen, nitrogen. And we can apply the same strategy to galaxies that we would apply to this gas cloud. And this has actually been done by astronomers for well over 100 years. And the key is that oxygen makes strong emission lines in the visible part of the electromagnetic spectrum. If we want to observe these emission lines in very distant, long ago galaxies, we need to go to the infrared. And as an infrared observatory, JWST is perfect for collecting such spectra from distant galaxies. Furthermore, the NIRSPEC instrument on board JWST is the ideal instrument tool for measuring It's the ideal instrument for measuring these emission lines from oxygen, including some very faint emission lines from oxygen that are needed to make the most robust measurements. And so I just want to finish up by showing you what we're actually going to do with JWST. So with JWST and the NIRSPEC instrument, we are going to measure the spectra of distant galaxies observed as they existed 10 billion years ago. And this figure shows an example of the spectrum of a distant galaxy observed as it existed in the early universe. Okay, so the light from the galaxy was produced in the visible region of the electromagnetic spectrum, but we are observing it in the infrared. This is actually a simulated spectrum that will be collected by JWST. And as part of our JWST Cycle 1 program known as Aurora, we will detect some really faint emission lines from chemical elements like oxygen, the one that we want to study. And these emission lines will enable us to constrain robustly for the very first time the amount of oxygen that is contained in these distant galaxies more than 10 billion light years away. And furthermore, we will gain very important insights into the galaxy formation process. And so I'm super excited about the measurements that we're going to obtain with the Aurora program, because I want to learn about how galaxies grow over cosmic time. So I'm going to stop there, and I want to turn things over to Professor Tommaso Treu.
Hello, Alex. Thank you. Let me share with you my presentation. Right. Let me see my presentation. All right, let's get going then.
Not yet. No, we can't see it yet. Try again.
Why? Let's see. How about now?
Yes.
Okay, thank you so much. All right, so we're going to continue our journey through space-time, and we're going to go back to cosmic dawn, the first galaxies, first light, and the fundamental question of the expanding universe, which leads back to the sort of question humans have been asking since the beginning of time, like what is the universe made of? And I'm going to tell you about the two programs that are aimed to answer those questions. So this is a cartoon describing what we think is the expansion history or cosmic history of the model in what we call the standard model of the universe. At the beginning of time, very shortly after the Big Bang, there's a phase called inflation. The quantum fluctuations on microscopic scale get blown up to gigantic scale. And shortly thereafter, we get the formation of the elements, and we get this what after some few 100,000 years, we see the origin of the cosmic microwave background radiation that you've probably heard of before. After that, there's a period of time that is called the Dark Ages. This period of time is called dark because there's really no source of light in the universe, no stars, no galaxies. And at some point, that Dark Ages period ends because the first stars form and the first galaxies form. And it's kind of like what we have here in Los Angeles during June gloom or May gray, when we have this fog, and as the sun comes out, it starts burning through the fog, and all of a sudden, the air becomes beautiful and transparent. And this is exactly what happens in the universe. It's kind of like this fog of neutral hydrogen that gets ionized by the first stars and galaxies and makes the universe transparent to UV radiation, which is what we see today as infrared radiation because of the effect of cosmological redshift. As this light travels through most of the history of the universe is expanding and stretching the wavelength of this light, and that arrives to us as infrared light. So this is a standard model, and there are two big questions that I would like to answer. One is, what is the universe made of? And the way to answer that is to understand the expansion history of the universe, because the expansion history of the universe is intimately related to its constituents. And the second question I'd like to answer is, when and how did the first galaxies form? Because I'd like to know when the universe goes from being opaque and foggy to transparent like we see today, and understand how the first stars and galaxies form. So this cartoon shows the expansion history of the universe. as a function of time. There's the Big Bang up to today, some 14 billion years later. And this yellow curve represents the distance between two arbitrary points in the universe. At first, the distance increases very fast. This is what is called inflation. And then gravity takes over, kind of like if you throw a pen or a ball up in the air, gravity from Earth will slow it down. And the same thing happens to the universe. The gravity from the matter in the universe slows down the expansion. And you see this yellow line bends over and becomes flatter. At some point, there's one mystery, and we still don't know why this happens. The universe starts accelerating again. This is equivalent to me throwing a ball up in the air, and the ball, rather than slowing down, keeps accelerating faster and faster upwards. This phenomenon is called dark energy, and it's puzzling enough, but that's not the whole story. How do we understand this? Well, in order to understand this, the best we have been able to come up with is that most of the universe is not made of the elements that Alice showed you in the periodic table of elements. So elements like oxygen, carbon, and so on and so forth, what we call ordinary matter, only make up 5% of the mass energy budget of the universe. A quarter of it is made of some other form of mass that we call dark matter, because the only thing we know is that it doesn't interact with light. And the remaining 70% of the mass energy budget of the universe is made of something called dark energy. And this is the substance that makes the universe accelerate. We don't really know what it is. There's no good theoretical explanation for what this can possibly be. But just to drive home the point, everything we know, like stars, planets, gas in between stars, gas in between galaxies, all of this stuff only makes up 5% of the mass energy budget of the universe. The rest is dark matter and dark energy. Now, you think this is crazy? Now listen to the next point. So in the past few years, people have been trying to measure the expansion history of the universe very precisely. The current expansion rate of the universe is called H0, where the 0 stands for now. And this is kind of like the current interest rates set by the Federal Reserve Bank now. So for the Fed, the interest rate is 1 or 2%. For the universe is 1 or 2 over 10 billion, right? Years. So the universe is expanding slower. It takes 10 billion years for the universe to double in size, but we can measure this rate pretty precisely. And we can measure it in two ways. One, we can measure it from the local universe by measuring it directly by seeing how fast galaxies appear to move away from each other. And the other way to measure it is go back to the early universe, measure certain properties, and then predict based on our understanding of the universe what the value should be at present time. And these two methods don't seem to match. Late time measurements, the ones that we do nearby, give a number of about 73 in some units, and early time measurements give a number of about 67 in the same units, which it's a pretty big deal. I mean, if this is true, this might be the beginning of a new cosmological model, in the sense that it is, for us, for a physicist, it's kind of like thinking that we throw a ball, we should be able to predict its trajectory if we know the how gravity works on Earth. And the same thing should be true for the universe. If we know the conditions in early time, we should predict the conditions at a later time, but we don't. So there's some missing ingredient and we don't know what it is. Now, of course, the problem is that we don't want to jump to conclusions. We're scientists, so we need to be really careful in our investigation. This is a big deal. We're claiming that there's something we don't understand of the universe, that we need a new particle or something. And so in order to be sure, we need to measure this expansion rate in many multiple ways. And I'm going to do it with JWST. And the title of my program is 100% gain precision and accuracy of the measurement of the Hubble constant from James Webb Space Telescope stellar kinematics of a lens galaxy. So James Webb, in addition to giving us beautiful images, is also a very, very powerful spectrograph. So for a lens galaxy like this one, when there is a galaxy bending light from a background quasar and creating 4 images, Hubble gives me just the images, But with JWST, I can measure how the stars in the galaxy move. And in the same way as when I measure the orbit of the Earth around the sun, I can figure out the mass of the sun, or when Professor Gresener group measures the orbits of stars around the supermassive black hole and can figure out the mass of the supermassive black hole. By measuring the motion of stars in this galaxy, I can figure out the mass of the galaxy itself. And this helps me understand the bending of light. And from the bending of light, I can understand expansion of the universe. There are a few steps in between, but the key part is that James Webb gives me the information that I need to do this. And this is a cycle 1 program, and we are hoping to get our data at some point in the second half of the year. And hopefully we can help resolve this thing that is called the Hubble tension that has been bothering cosmologists for a few years now. The fact that we cannot really reconcile these two measurements of the Hubble constant. The second part, the second program, is related to understanding better this phase called cosmic dawn. How do we go from cosmic dark ages where there is this fog of neutral hydrogen to a transparent universe made of ionized hydrogen? So we think the stars and then galaxies were the ones providing the bright lights that burn off the fog, but we don't quite know exactly when and how that happened. And the reason is that Hubble really was just able to touch it. So Hubble was able to tell us it's gotta be before a certain time, but we can't really see the first galaxies. With James Webb Space Telescope, we can not only see the first galaxies, but we can also start to measure their properties like oxygen abundance and all those sort of things to convince ourselves that they really are the first galaxies. Like if they're the first galaxies, they should have no oxygen because oxygen was formed during galaxy evolution. But this is difficult because these galaxies are very faint, even with JWST. So we use a trick. That trick is called gravitational lensing. So instead of looking at the galaxy directly, we look at a galaxy behind a cluster of galaxies. This is a group of maybe 1,000 or more galaxies, a few billion light years away, more or less halfway between Earth and the distant galaxy we want to learn something about. And this cluster of galaxies is bending space-time so that light rays get to me over these bent trajectories. And the effect, the net effect is that it's kind of like having a magnifying glass. So the galaxy in the background appears to me, to the observer, bigger and brighter than it would be without. So it's kind of like having James Webb Space Telescope and then another telescope behind it. But that other telescope is a cluster of galaxies, something that nature itself provides. So this is our telescope, is called Abell 2744. You see, this is an image from Hubble. There are like thousands of galaxies here. The mass is something like 1,000,000 billion times the mass of the sun. So it's like a huge mass concentration. And that bends all the light from the background and allows us to see the first galaxies ever to form and take their spectra so as to measure their chemical composition and their properties. The name of the program is Through the Looking Glass, and it's fairly long, so I won't read it all, but it's one of those 13 programs called early release science programs. So these are supposed to be taken first by the observatory. So it might be one of the very first programs taken. And one of the conditions is that all the data will be publicly available. So we are taking this data as soon as possible, maybe even in June or July, and we will do our best to make them public and understandable to the community, because we want everyone to understand the power of this telescope as soon as possible, so we can make all of us as a community, we can make best use of it during its finite lifetime. And so this concludes my presentation, and hopefully in 6 to 12 months, we will have some results. But in the meantime, I'm happy to introduce a Q&A session with my colleagues, Alice, Matt, and the Dean and the other members of the Dean staff that are helping us put this together. Thank you very much for listening, and I look forward to your Q's and A's. I'll stop sharing my screen.
Wow, I'd like to thank all our three speakers for fantastic presentations. This is so exciting. Certainly a lot of really great things are going to happen. I've been monitoring the Q&A section, and you have already answered a number of really interesting questions. So in the benefit of time, I'd like to ask a question that will go for all three of you, so you'll have a chance to respond. And I think we'll do it alphabetically with Alice first, Matt second, and Tommaso third. So the general question is, how will the observations provided by the telescope change astronomy as the first part? And what opportunities will it create, not only for faculty, but also for students now at UCLA and in the future? Alice.
Oh, what a great question. Thanks so much, Miguel, for asking this question. I think one of the things, okay, so I'm gonna say just generally like how JWST will change things for astronomers studying the early universe is that the Hubble Space Telescope has made great progress over the past 10 plus years in finding galaxies within the first billion years of cosmic time, we would say beyond a redshift of 6. But the thing is, the vast majority of observations that we have of this early time in the universe are just images of these galaxies. So we actually haven't measured the precise distances and contents like the stars and the gas and the physics in these galaxies during this first billion years of cosmic time, you know, that Tommaso was talking about in terms of the ionization and the cosmic dawn. And so JWST, by giving us spectra, will allow us to probe the physics and actually understand the nature of star formation in the first stars. So I think that's the impact sort of on an intellectual level it'll have for those of us studying on the early galaxies. And someone asked a question about extrasolar planets, I think. So JWST is also going to be transformational for the study of atmospheres of planets outside our solar system and their composition. And so these are some of the intellectual leaps that are going to happen from JWST. Now, in terms of students, we're all in the midst of the budget process for JWST, because when you get time on this majestic observatory, NASA is also very generous or somewhat generous and grants you funding to analyze the data. And so I think all of us here at UCLA are really excited that we're actually going to be supported by NASA in analyzing our beautiful data. And so I'm looking forward to supporting some graduate students over the next few years in analyzing our aurora spectra.
Well, that's really exciting. Thanks, Alex. So Matt.
Glad you asked Alice first. She really hit it so well. Could I just mention on the graduate students, because I can't say too much more than Alice did, but I haven't looked at everybody's budgets, but I know my budgets. The number one item on there is support of graduate students. That's what we really need. Now, maybe the number two item for it might be to hire a postdoctoral research associate. And they're wonderful to have in the department. It's very exciting and lively. You've got some great ones here, but I would like to point out they're a lot more expensive. And graduate students at UCLA are ready to take on every aspect of this. They are already ready. I mean, they're basically professional astronomers now, and that gives us an enormous advantage. Actually, I really feel quite badly for a lot of our colleagues who work at otherwise brilliant astronomical institutions, observatories and so on, that they can't work with graduate students. They can't have access to the kind of collaborations that we can. It just gives us an enormous edge. And so that, honestly, that's our priority, certainly for me, but I think for most people at UCLA too. On the discoveries, I mean, Alice said it very well. Of course, you want to measure things more precisely and more delicately than you ever have before. But the serendipity is sometimes you just see things that just couldn't have been there before. You know, the new emission line, she's looking at things that have almost never been seen before. That is so exciting, just the moment that you see it on your display screen. I just remember the first, you almost remember where you're sitting the first time you see some of the Hubble images. I mean, the first deep field, like Alice said, it was just a picture, but man, that picture showed such exquisite detail. And it was immediately obvious that galaxies are nothing like galaxies today. Look at that picture. Yeah, I know what galaxies look like. I've looked at all the atlases of local galaxies, and it wasn't like I was looking at anything. They're so messed up. They look just, like I said, like little teensy fragments. They really look like kind of shrapnel to me. That's not a very technical term. I mean, it was immediately obvious that some remarkable things have been going on. Basically, galaxies apparently have built by eating other galaxies that the Milky Way must have eaten. I don't know. That's some also. Many big galaxies and dozens of little ones. You can see that still happening. So sometimes a discovery, and this is, JW is going to do this every week. You just look at the first data and you say, wow, I didn't even know we were going to see that. What the heck does it mean? And sometimes, of course, you've got a bigger question than you did when you started, but that's usually when progress starts making.
Yeah, that's great, Matt. I want to take this opportunity to comment, how so many people in the community, alumni and friends of UCLA have really contributed and continue to participate in many of the activities that our students do. They really enable things that would not be possible if we just were to operate on state funds. And I think that is fantastic. It's so exciting, right? So yeah. So Tommaso, please tell us what you think.
Well, okay, so I think, and I want to tell a little personal story here that when I was an undergraduate, I think, or I just graduated from college, I went to my first conference, was the Science Drivers for the Next Generation Space Telescope. It wasn't called JWST back then. It was 1998. And it was a dream, like, can we build a telescope that is much better than JWST? What would be the science questions that we'll answer? Now, probably like 3/4 of the science questions are just superseded or wrong or whatever. But the amazing thing is that 24 years later, we have that telescope. So I think the biggest gift to my students and postdocs is that they will be able to use this telescope. They will be able to be among the first ones to use this telescope. And I tell you, there's two reasons why I do this job. And I think this is true for my colleagues as well. One is that nothing beats the joy of discovery.
Yeah.
Like when you discover something, it's like ecstasy, it's like the best joy you can ever. And the second is that the kind of discoveries that we make don't really have an immediate application, but they change the way in which we think about the universe and we think about our place in the universe.
Yeah.
Like, realizing that there's like billions of other galaxies, or that, that all our elements that are in our body come from stars, or realizing that the universe is made of particles that are not the electrons and protons in our body. I think these are the things that give us a sense of our place in the universe. That on the one hand, we're very little human beings, but on the other hand, we have these brains that can conceive these things that are so much bigger than ours. And I think this is the biggest gift that JWST gives to our students and our postdocs, like this sense of perspective both ways.
Yeah, no, thank you. I think you're right. Just the level of satisfaction that one gets from knowing about one's place in the universe is just so enormous. And as far as our students, I think just their overall preparation, the talent, the number of things that they know and they can use in so many different areas of technology, of society is really impressive. I think really what you guys do is making our world a much better place, and one that we can begin to understand a little bit more. And that is just incredibly exciting. So I'm totally looking forward to see what happens in the next few months and then the next few years of your research and your discoveries. And I'm definitely going to be here for the second part of this webinar. So this would be probably a good time to go to transition into the next part. But I like to tell the audience that if you are interested in staying for an additional 30 minutes of questions and answers, Professor Matt Malkan and Alice Shapley, I don't know if Tommaso will be able to stay, but we invite you to click on the link on the chat. You can see the link right there to navigate to a Zoom meeting. And they look forward to continuing to answer your questions there. So I'd like to thank you for attending tonight's program. We look forward to seeing you virtually again at part 2 of our webinar series, The Next Frontier for UCLA Astronomy with the James Webb Space Telescope in the spring. Please keep an eye out for an invitation in a couple of months. Thank you, our panelists, and everybody have a wonderful evening. It's very good to have you join us. Bye-bye.